Okay, so today we will be talking about, first of all, the topic as usual, quantum mechanics. Okay, for today we will be talking about different processes of quantum mechanics. Like in basic, I will be talking about what is light and everything regarding light. It could be it's many things, of course. So when we talk about what is light, in simple words, people will take light as a way to see things, something which is required to see something. But today's video we will only talk about complex version of light, version of light, the real science behind what is light. First of all, we will talk about light being wave and light. So the properties of wave is when it is not observed, as all the particles have this property in quantum mechanics. Second, light is when it is observed. Particle is when it is observed, and then, so what I mean by here is that what will be property of light when you're observing, when you're not observing and observing the light, because it is different for each point. Okay, then we can also talk about uh, how light is in terms of particles. Of course, in terms of particles, it is E equal h f. That light is, this is also, we can in simple words we can say it's photon, because one photon is equivalent to some kind of energy, and we can expand this equation to get E equal h c over delta, lambda. What does this equation show? That photon is nothing but energy which of course move at the speed of light. It is which it moves at this value, 3 times 10 to the power 8 meter per second. Okay, then let's talk about something advanced. Now we will talk about Bohr's model. Bohr model, because it involves light, so we will talk about it. First of all, what is Bohr's model? Bohr's model is a way to show how the atomic structure is, how the atomic structure looks like. And for this, the best example we take is hydrogen's example, hydrogen. Okay, now we will assume that hydrogen has this is hydrogen's structure, atomic structure, and it has an electron, which is 1, of course. And now there's something known as hydrogen spectra. Okay, hydrogen spectra. Hydrogen spectra, yeah. So when a body is heated, it gets energy, right? It has inner heat energy. What happens that it emits electromagnetic radiation. The radiation may consist of various components having different wavelengths. Mean different wavelengths mean the lambda is varying. Varying. Okay. If the emitted light is passed, okay, then of course we also know that light. What is light? Light is of different. Wait, sorry. Different colors. Colors, and those colors are is related to lambda of light because it is of 7 colors. Okay, so a hydrogen sample also emits radiation. This is where we get the topic hydrogen, uh, with wavelengths less than those in the visible range, and also with wavelengths larger than those in the visible range. So we see that lines may be grouped in separate series. In each series, separation between the consecutive wavelengths decrease as we go from higher wavelength to lower wavelength. What I mean by is that uh, we'll talk about this over here. Let me just, as we go higher in wavelength, the distance between these in the spectra, this distance is increasing. This being 90, that's I suppose, and this being 120 nanometers. Let me 1 nanometer equal 1 times 10 to the power minus 9 meter. And so now let's talk about Bohr's model in detail. In 1913, Niels Bohr, of course, then again Niels Bohr. Who is Niels Bohr? The one who is involved in quantum mechanics as well. A great name in physics, suggested that puzzle of hydrogen spectra may be solved if we make the following assumptions. Okay, now we'll be making some assumptions. What are those assumptions? I will not write all of them. I'll just take the key points. The electron revolves round the nucleus in circular orbits, meaning if this is a nucleus, this is the electron revolving, or this is here we have a electron revolving. Okay. Second assumption, the orbit of the electron around the nucleus can take only some special values of radius. In these orbits of special radii, the electron does not radiate energy as expected from Maxwell's laws. These orbits are called stationary orbits. What I mean by certain values of radius is that this has certain value of radiation, radius. If it goes here, the radius again has a certain value, it doesn't have any value which is odd. Third assumption, the energy of the atom has a definite value in a given stationary orbit. So the energy in this orbit will have a definite value. Definite mean it will be a one single value, not any range of values. The electron can jump from one stationary orbit to other if it jumps from an orbit. Of course, again, if it jumps from an orbit means either goes up in orbit or down in orbit. Now here we have two issues, two things, scenarios. If it goes up in orbit, it gained electron, gained photon or energy up. If it went down in orbit, it means emit photon. Did I say electron the previous one? Sorry, photon, which is down. So now that photon, the energy of this photon can be calculated with the energy levels. This is how we take the energy levels as. This is energy level 2 and this is energy level 1. So if from here till here the change in energy is what is the energy of the photon, E2 minus E1. And one more thing, this E1 is also known as ground state, we call them energy state or energy level state, ground state or ground level or excited level. No, wait, lowest level, sorry, not excited is when it will go up in a circular orbits. I'm just taking this line, so this is how it works. Okay, the wavelength of the emitted radiation, means the one with the photon being lost, is given by the Einstein-Planck equation, which we can write as E2, this E2 minus E1 equal hc over delta. I think we just said over here this equation. So in this equation, this is the same as saying E equal hc over lambda, and again E equal hf. It's just they expanded it. The electron can also observe, as I said, some source and jump from lower energy level to high energy level. So observe, increase in level, emit, decrease in level. Then again, one more assumption: in stationary orbits, the angular momentum of the electron about the nucleus is an integral multiple of the Planck constant. So if divided by 2 pi, so no, not this h bar, is h bar or h only, sorry. So this L can be seen as nh over 2 pi. This last assumption is called Bohr's quantization rule, and the assumption A and D are known as Bohr's postulates. Okay, so then energy of a hydrogen atom. Now we get the real deal in. What is here? I think quantum mechanics takes place. Let us now use the above postulate. We will be using the assumptions we made in the last one to talk about the hydrogen atom. So let us assume that the nucleus has a positive charge, which it has, and that charge is known as Ze. There are Z is the proton number, and an electron moves with a constant speed v along a circle of radius r, with the center at the nucleus. The force acting on the electron is then known as F equal Ze r square over, not r square, Ze over 4 pi. This is a one, I think, symbol, r cube. And the force acting on the electron is that due to Coulomb attraction and is equal to what I just wrote here. This is how we can calculate the force of an electron moving in an atom. The acceleration of the electron is towards the center. Again, this is common Newtonian physics. We are just applying it here. And has a magnitude of v square over r. If m of the mass m is the mass of the electron from Newton's law, we can write it as equals to m v square over r. And then when we take r as, let's suppose we take r as a this r and this r cancels each other, so we get r equal 4 pi, or wait, what, sorry, z e square over 4 pi. This is another way of writing this equation, mv square. Also, from Bohr's assumption, quantization rule, the angular momentum is again angular momentum mvr equal n h over 2 pi, and this is another way of saying angular momentum L equal momentum times distance. This is the way we say it as L R, and the momentum is in this direction, m equal mv. Okay, then where n is a positive integer, and you have noticed that we are using n because here the law that energy is discrete comes in Planck's law, so we take n as, we are talking about energy and we know energy is discrete, so we take n as n will be there to show that energy is discrete. Eliminating r from I, from this one r, if we eliminate r, we get v equals z e square over 2 this and h n. Substituting this into this, okay. So, and then go so on. Okay, then let's go into the complex level, or what else could we talk about in this? Okay, yeah, let me just say one thing. This is energy level 1, energy level 2, and it depends on the atom and which, how many energy level it has. Okay, so then talking about the quantum mechanics of Bohr's model, the electron. Here we'll take the special example, electron. So here we'll have wave function, introducing wave function finally. Physicists now have a mathematically and logically sound theory, which is known as quantum mechanics, which describes the spectra in such a better way, which a very brief introduction to this theory is given below, as I'm doing something. So we have electric field, which is common, as well as the particle picture, which is, we will not take a particle as an electric field, which is waves, and particle picture, which is one single point. The energy of a particular photon is related to the wavelength of the energy wave. Light going in x direction is represented by the wave function. I'm just integrating this as with E of x and t equal E0, this is just energy, sine kx minus wt. In general, if light can go in any direction, so here we are specifying x, as it means it has certain direction, but if it can go in any direction, we can write r, this r shows that any direction, equal E of 0, this is S mass, sine k any direction, r any direction, minus wt. Okay, if I take energy square at a certain point r is large, the intensity of the light is high, and we say the density of photons of that at that position. Density means the number at how many we have. If I take energy, if I take okay, sorry, if I take energy square, okay, this shows that in a certain area, in a certain field, let's suppose this field, the higher the value of this, the higher the value, the greater. Again, probability takes place because quantum mechanics is all about probability. The greater the density. We're not saying it will be there, it's basing the greater maybe. So again, then probability is taking place. Okay, so where this photon at time t, we can't assign a unique position to the photon because energy is spread out over a large space, so we cannot just give it a unique value. And wherever energy is not zero, equal or not equal to zero, there is light. But if we put an instrument to detect the photon, we shall not detect it in a whole region, we detect it at certain point. And here we have one thing to talk about, that light can, this is how I think of it, light can know when it is being watched. Okay, it will, when we talk about light, it will know where you when you're going to watch it and when you're not going to watch it. Similar is the case with electron. Electron also have a wave character as well as a particle character. Its wave function. For electron we take it as psi again. Same thing, just difference is that we're using psi here. And which may be obtained by its wave function is this, and this is a wave function which can be obtained by using Schrodinger's wave equation. The particle properties of the electron must be understood through this wave function. The wave function varies continuously in space and may be extended over a large part. This does not mean that the electron is spread over the large part. If we put again same thing with detector, and it will be in one place. If I write the quantum mechanics, the Schrodinger equation for hydrogen atom, I will write minus h bar, or only h, square over 8 pi square m. Then we get partial derivative square of x and so on, with the same thing, but we'll just change the x with z, y and z, minus ze square psi of 4 over 4 pi of this symbol r equal to energy. This is the potential difference of hydrogen atom. Okay, we'll not talk about detail of it because it will be a lengthy topic. So then, and the difference between it is that in a Schrodinger equation, the